The last of our 3 videos on approximation is on Newton's method, which involves iteration, which is the repetition of an algorithm over and over again to increasing levels of accuracy. So what we are going to look at now is how to use Newton's method to find the root of an equation. So let's say we have a function, okay, and we draw our function, and we know that there's a root somewhere in a region. So we would say, take a guess, x naught. Okay. So our question, where is the x-intercept? We guess. Our guess is x naught. Then what we will do once we have taken a guess is we're going to draw the line tangent to f of x at x naught. Draw tangent to f of x at x naught. Okay, so let me go right here. We're going to draw our tangent. Okay, so f prime at x naught is going to be equal to, and we're going to look right here, it's going to connect with that point down there, f of x naught minus 0. Okay, so this point right here, we're going to call it x1. So it's another x value, but it's at 0. So the slope of that tangent line is going to be f of x naught minus 0 over x naught minus x1. Okay, so difference in y's minus difference in x's. Okay, just finding the slope. So x1 is going to be equal to x naught minus f of x naught over f prime of x naught. So all we're doing is multiplying both sides, dividing by f of x, f prime of x, and then subtracting, adding x naught to both sides. Okay, so x1 is going to be a better guess. No matter where it is, it's going to be a better guess of x-intercept. And now that we have x1, we can go right up here and have our x1, draw a tangent line, and find an x2 that is going to be even closer, and find an x3 that's going to be closer than that until we get xn, and we can just keep doing that n times. So that would look like x2 is x1 minus f of x1 divided by f prime at x1. And keep on going, x sub n is going to be x sub n minus 1, so the x before, minus f of x sub n minus 1, so f of the x before, divided by f prime of the x sub n minus 1. Okay, so we're using each successive x we find as the starting point for finding an even better x. Okay, so let's look at example 1. And this is another method, but this method is specifically for finding roots. So you notice that we're banking on the fact that the y value is going to be 0 when we've created this formula for xn. So if we're going to solve different kinds of estimation problems, we need to make sure that it is to find a root. So let's use Newton's method to find the 6th root of 3 correct to 3 decimal places. Okay. So what we want to turn this into a question that involves finding the root. Okay, a root. So we have x equals the 6th root of 3. Okay. So we want to make this into finding where a function equals 0. So let's rewrite this. We can raise both sides to the 6th power. So that means x to the 6th has to equal 3. That means that x to the 6th minus 3 is 0. And now we are looking at finding the 0 of a function. Okay, so we're going to let f of x equal x to the 6th minus 3. And we're going to try to work out where that is equal to 0. So f prime of x equals 6 x to the 5th. So where are we going to start with our guess? Okay, well, the 6th root of 3, we know it's going to be smaller than 3. We know it's going to be bigger than 0 because it's a 6th root. We're looking at the positive 6th root. So we're going to guess, and we know it's not smaller than 1 because that would make it a fraction. So let's take a guess that it's between 1 and 2. It's either going to, and this, considering the square root of 3 is between 1 and 2, it's a reasonable guess that it's going to be between 1 and 2. Let's confirm that that works. We can use the IVT because this is a continuous function. So let's see, f of 1. 1 to the 6th minus 3 is negative 2. And f of 2, well, 2 to the 6th minus 3 is going to be 64 minus 3, which is 61. So by the IVT, root exists, is between 1 and 2. So let's take a guess. I'm going to guess that my x naught, and it doesn't actually matter what you guess to start with. If you guess something different, you will eventually get there. You will eventually get to something that is going to be a better guess. So let's say x naught equals 1.1. Okay, so we're going to try to find an x1. So x1 is x naught minus f of x naught over f prime of x naught. And so it's, which is 1.1 minus 1.1 to the power of 6 minus 3 over 6 times 1.1 to the 5th. Okay, and when I simplify that, I would, being a modern person, would actually use a calculator. We get 1.227. Okay, so let's try our next iteration. So we have a guess. Let's make that, we took one guess, we made it a better guess. Let's make that an even better guess. So x2 is x1 minus f of x1 over f prime of x1. And that is 1.227 minus 1.227 to the 6th minus 3 all over 6 times 1.227 to the 5th. We don't need to compute the derivative again. Derivative is the same, function is the same, just changing what we're plugging in. So we get 1.202. Let's look at x3, which is x2 minus f of x2 over f prime of x2, which is 1.202 minus 1.202 to the 6th minus 3 over 6 times 1.202 to the 5th, which equals 1.201. We can try an x4. I'm not going to write everything out. We get x3 minus f of x3 over f prime of x3. And here we get, again, 1.201. So we would probably have to keep going a ways. We're probably at this point pretty accurate to the third decimal place once you get the same number twice in a row. And in fact, the 6th root of 3 is equal to 1.2009. So that is accurate to one decimal place, to 1.201. Okay, so that's one example. We can find a root by constructing an equation and then using that equation and its derivative to apply Newton's method. What else can we do with it? Well, we can approximate intersection points of graphs. So we're going to here approximate the x values of the indicated points of intersection of f of x equals 2x squared minus 1 and g of x equals cosine x. So let's sketch that. So we have a 2x squared minus 1. That is going to look like that. This is minus 1. Okay. And we have our cosine x, which is going to cross at pi over 2, which is just around 1.5. So negative 1 is here, and 1 is here. And we're going to have some kind of cross like right here. Whoopsie. That was not a really good cosine x because it is totally supposed to be symmetric around the y-axis. Let's make that a better sort of cosine x. Okay, not my best cosine x, but it'll have to do. So we have 2x squared minus 1 equals cosine x. So what we want to do is this is how we would try to solve this equation, but I don't know how to solve this equation. What we can do now is we can use Newton's method to try to approximate the solutions to this equation. So let's make f of x equal 2x squared minus 1 minus cosine x. Let that be some f of x. We're going to try to find the root of that the 0 of this function. So the derivative f prime of x is 4x minus 1 goes away, plus sine x. Okay, so let's take a guess and say maybe these are around 1. Okay, so we're going to let x naught equal 1. Okay, so x1 equals x naught minus f of x naught over f prime of x naught. So really this is just a lot of plugging in if you've got this equation memorized. And then x2, same thing with x1. For this one we get 1 minus 2 times 1 squared minus 1 minus cosine of 1 over 4 times 1 plus sine 1, which is 0.905. And this is x2, which is x1 minus f of x1, or f prime of x1. And I wouldn't be surprised if graphing calculators use something like that to help you find the intersection of points, because this is an iterative method that they can apply. Computers do this really well, which is applying the same thing over and over again. It's an algorithm. Okay, so x the 1 minus f of x the 1. When we plug all of that back in, we get 0.90038. Okay, x cubed, we do the same thing with x3, do the same thing with x2 minus f of x2 over f prime of x2, and we get 0.90037. Okay. And since these are both even functions, we had the one root, so that would mean our two solutions are approximately equal to 0.90037 and negative 0.90037. And we know this because cosine of x and 2x squared minus 1 are both even functions.